This video will focus on convolution sums in discrete-time LTI systems, and it's probably worthwhile to take a few minutes and explain what an LTI system is. We all know what a discrete system is. A discrete system, discrete-time system, is a system that basically is a sampled values in time at n equal to 1, 2, 3, or whatever. And the LTI system, on the other hand, is a property of these systems that we need to talk about. So LTI stands for linear time invariant system. So basically what we are saying is that our system is linear, which means the output and inputs are linearly proportional. And then we're also talking that is time invariant, which we're saying over time it does not change. These are nice assumptions to have when we're getting started and trying to learn the concepts of how signals and system works. And we're actually going to maintain these two assumptions throughout the series, signals and system series of lectures that are provided here. The focus of this video is on a convolution sum. But before we get into talking about convolution sum, we need to kind of introduce some basic ideas that help explain why convolution sums are useful, and also will help us talk a little bit about why we want to take a look at convolution sum. So if we were to take in physical world, we make a mold of an object, and then we can use that mold to pour plastic into it. That plastic will take the shape of the mold, and then we have the product. So the mold's job is to take raw plastic, melted plastic, and shape it into what we like. System does exactly the same thing, except is doing it with signals, with voltages and currents. So the job of a system is to take a signal, shape it to whatever shape you want. Now, how do we know what that mold looks like, or how do we describe that mold for an electrical system? The way we do it, we'll take the system, whatever system somebody gives us, some system someone gave us, and we put in here basically a input that is all impulse function. So it would be delta n minus k, and this input goes from minus infinity to plus infinity. So if you plot this discrete function, you will see that this discrete function is a very uniform set of values, always 1, from minus infinity to infinity on the n-axis. So in a sense, what we are doing, we'll send a very uniform signal into whatever shaping the signal comes out. It's going to be because the system shaped it to that. So what comes out of here, we're going to refer to it as h of n. And the name for this would be an impulse response. This is basically the mold that we are looking for, okay? So this is the shape that we can use later on to like for a mold where we pour the plastic into the mold and took the shape. In this case, our mold is going to be h of n, which is called the impulse response, is that we can call it mold, and we can literally push our signal through h of n, and we can get the output we are looking for. Okay, that process of pushing electronic signals into another electronic signals we have named convolution. So now that we know how we can take a system and find the impulse response of that system, now we can go and talk about the next step in the process. Now, if once I know my system and I know its impulse response, then if somebody gives me an x of n, that would be the physical analogy of a mold. That would be the plastic pouring through the mold. What comes out at the other end in the physical world would be the object I'm looking for. In here is going to be my output signal, right? Because now I know how the system shapes it. I can put it in and do that. But now, just like mold, where either the mold has to move or the material has to move through each other. One has to move so they go through each other. The H of n and X of n somehow got to be pushed over each other. So one interacts with the other one. Typically, they say X of n is pushed through H of n to get Y of n. So we have a name for that. We basically says that Y of n is the convolution. That pushing process is called the convolution of X of n with H of n. Now, if you sit down and think about how do we take one signal and push it through other signal, it's basically pushing means to multiply them by each other as they go by each other to take the shape. Multiplication is how we make one signal take on the shape of the other signal. So a convolution such as this, it's mathematically, if you want to talk about that movement, mathematically that convolution sum is k going from minus infinity to infinity, x of k, notice h's are replaced with, n's are replaced with k, and then h of n minus k. Notice what happens. As n grows, you will see that this h of n minus k keep moving to the right. And that's how we're running them together. So this star from here on is not a multiplication for us, but rather we refer to this as a convolution. Now, it's the same as the physical world, where it really doesn't matter whether the mold is moving and the plastic is constant, or the plastic is moving and the mold is constant. Either way, when they interact with each other, that's when we start to get, either in the physical world, we're getting the product, the part that we're looking for. In the case of electronics, we're getting the output we're looking for. And this is called the convolution sum. This piece, as the name implies, this is the convolution sum. And this is the one that gives us the output. Now, remember that k variable is the k, and inside the summation is a constant. That's something to remember. Okay, now one properties of convolution we should talk about here before we go too far is that the convolution has associated property. In other words, it doesn't really matter whether the mold is moving or the input is moving. It doesn't matter whether the impulse function is moving or the input is moving. The answer is the same. So if the input is moving, as opposed to the first case where the mold was moving, you still get a y of n. So these two are equivalent to each other, these two equations. So if you want to do that here, then the convolution sum for this one look very similar to that, except instead of h of n moving, in this case x of n moves, and watch what happens. Oops. Was copying the first function too much. So h of k would be constant, and then x is the one moving. The result again is the same. Both of these are called, this is also called convolution sum, and they are equivalent to each other. Now, once we get this far, solving this also and finding y of n could be mathematical. We can take two approaches. One approach, we basically apply pure mathematical equation without any of our intuition or graphical help, and that is called the analytical or mathematical approach or solution. The other option, the other way we can solve this and get the final answer, is the graphical or the intuition. Okay, both of those methods are just fine, and we're going to have some example later on where we take a simple x of n and h of n, and we show how you could use graphical or analytical approaches to solve this issue. Okay, so look for videos later on where we would have example of, finding y of n using graphical approach or using analytical approach to find y of n in the next couple of slides. That brings us to the end of this particular study. The goal was to basically introduce convolution, and we have introduced it.